Next, we'll talk about percentiles and moments. Percentiles, you hear about that in the news all the time. People that are in the top 1% of income, that's a percentile. We'll explain that and it has some examples there. And we'll talk about moments. Very fancy mathematical concept, but it turns out it's very simple to understand conceptually. So let's dive in and get started. Let's talk about percentiles and moments, a couple of pretty basic concepts in statistics, but again, we're working our way up to the hard stuff, so bear with me as we go through some of this review. So percentiles, basically if you imagine that if you were to sort all of the data in a data set, a given percentile is the point at which that percent of the data is less than the point you're at. So a common example that you see talked about a lot is income distribution. When we talk about the 99th percentile or the 1%ers, imagine that you were to take all of the incomes of everybody in the country, in this case the United States, and sort them by income. The 99th percentile would be the income amount at which 99% of the rest of the country was making less than that. Okay, so that's a very easy way to comprehend it. This is some real data here. So for example, at the 99th percentile, we can say that 99% of the data points here, which represent people in America, make less than $506,000 a year, and 1% make more than that, conversely. So if you're a 1%er, you're making more than $500,000 a year, roughly. Congratulations. But if you're a more typical median person, the 50th percentile defines the point at which half of the people are making less and half are making more, which is the definition of median, right? So the 50th percentile, same thing as median, and that would be at $42,000 given this data set. So if you're making $42,000 a year in the US, you are making exactly the median amount of income for the country. And you can see, the problem of income distribution here. Things tend to be very concentrated toward the high end, which is a very big political problem right now in the country. So we'll see what happens with that, but that's beyond the scope of this course. So that's percentiles in a nutshell. Percentiles are also used in the context of talking about the quartiles in a distribution. So if you're looking at, say, a normal distribution here, people talk about quartiles, and quartile 1 and quartile 3 in the middle are just the points that contain together 50% of the data. So 25% are on this side of the median and 25% are on this side of the median. The median in this example happens to be near the mean. So for example, the interquartile range, when we talk about a distribution, is the area in the middle of the distribution that contains 50% of the values, okay? Now this is an example of what we call a box and whisker diagram, so don't concern yourself yet about the stuff out here on the edges. That gets a little bit confusing and we'll cover that later. Even though it's called quartile 1 and quartile 3, they don't really represent 25% of the data, but don't get hung up on that yet. Focus on the point that these quartiles in the middle represent 25% of the data distribution, and those tend to be in the middle. Let's look at some more examples using Python and kind of get our hands on it and conceptualize this a little bit more. All right, let's get our hands dirty with percentiles. Go ahead and open up the Percentiles IPython notebook file if you'd like to follow along. And again, I encourage you to do so because I want you to play around with this a little bit later. So let's start off by generating some randomly distributed normal data, or normally distributed random data rather. And in this example, what we're going to do is generate some data centered around 0, with a mean of 0, with a standard deviation of 0.5, and I'm going to make 10,000 data points with that distribution. And we're going to plot a histogram and see what we come up with, and it looks a little bit something like that. Very much like a normal distribution, but because there is a random component, we have a little outlier here. Things are tipped a little bit to the right here, a little bit of random variation there to make things interesting. Now, to compute the percentile values of this distribution, NumPy provides a very handy percentile function that will do that for you. So we created our vals list of data here using numpy.random.normal, and I can just call np.percentile to figure out the 50th percentile value in this example, and that turns out to be 0.005. So remember, the 50th percentile is just another name for the median, and it turns out the median is very close to 0 in this data, and you can see we're tipped a little bit to the right, so that's not too surprising. If I want to compute the 90th percentile, that gives me the point at which 90% of the data is less than this given value. So the 90th percentile of this data turns out to be 0.65. So it's around here, and basically at that point, 90% of the data is less than that. So I'll believe that. 10% is greater, 90% is less than, right around there. And the 20th percentile value, that would give me the point at which 20% of the values are less than that number that I come up with. So the 20th percentile point works out to be negative 0.4 roughly. And again, I believe that. So it's saying that 20% of the data lies to the left of negative 0.4, and conversely 80% is greater. So if you want to get a feel as to where those breaking points are in a data set, the percentile function is an easy way to compute them. If this were a data set representing income distribution like in our slides, we could just call np.percentile vals, 99 and figure out what the 99th percentile is. So you could figure out who those 1%ers people keep talking about really are, and if you're one of them. All right, now to get your hands dirty, I want you to play around with this data. So this is a IPython notebook for a reason, so you can mess with it and mess with the code. Try, different standard deviation values, see what effect it has on the shape of the data and where those percentiles end up lying, for example. Try using smaller data set sizes and add a little bit more random variation into thing. It's just get comfortable with it, play around with it, and find that you can actually do this stuff and write some real code that works. So spend a few minutes playing around with that, hit pause while you do that, and when you continue, we'll come back to the concept of moments of data distribution. Next, let's talk about moments. Moments are a fancy mathematical phrase, and you don't actually need a math degree to understand it, though. Intuitively, it's a lot simpler than it sounds. It's one of those examples where people in statistics and data mining and machine learning and data science like to use big fancy terms to make themselves sound really smart, but the concepts are actually very easy to grasp, and that's the theme you're going to hear again and again in this course. So let's talk about moments. Basically, it's ways to measure the shape of a data distribution, of a probability density function, of anything, really. And mathematically, we've got some, really fancy math notation here of how they are defined. And, if you do know calculus, it's actually not that complicated of a concept. We're taking the difference between each value from some value raised to the nth power, where n is the moment number, and integrating across the entire function from negative infinity to infinity. But intuitively, it's a lot easier than calculus. Ready? Here we go. The first moment works out to just be the mean of the data that you're looking at. That's it. The first moment is the mean, the average. It's that simple. Second moment is the variance. That's it. The second moment of a data set is the same thing as the variance value. And, it might seem a little bit creepy that these things just kind of fall out of the math naturally, but think about it. The variance is really based on the square of the differences from the mean, so coming up with a mathematical way of saying that variance is related to mean isn't really that much of a stretch, right? It's just that simple. Now, when we get to the third and fourth moments, things get a little bit trickier, but there's still concepts that are easy to grasp. So the third moment is called skew, and it is basically a measure of how lopsided a distribution is. So you can see in these two examples, if I have a longer tail on the left, that is a negative skew. And if I have a longer tail on the right, that's a positive skew. So you can see here what the shape of a normal distribution would look like without skew. If I stretch that out on one side, then I end up with a skew, or on the other side, a positive skew in that example, okay? So that's all skew is. It's basically stretching out the tail on one side or the other. And it is a measure of how lopsided, how skewed a distribution is. The fourth moment is called kurtosis. Wow, that's a fancy word. All that really is how thick is the tail and how sharp is the peak. So again, it's a measure of the shape of the data distribution. And here's an example here, and you can see that the higher peak values have a higher kurtosis value. So the red curve has a higher kurtosis than, this, is that black? I can't even tell. Blackish brown curve here at the bottom. So it's a very subtle difference, but a difference nonetheless. It basically measures how peaked your data is. So again, to review, first moment mean, second moment variance, third moment skew, fourth moment kurtosis. You already know what mean and variance are. Skew is how lopsided the data is, how stretched out one of the tails might be, and kurtosis is how peaked, how squished together the data distribution is. So let's play around in Python and actually compute these moments and see how you do that. Okay, to play around with this, go ahead and open up the moments IPython notebook file, and you can follow along with me here. So let's again create that same normal distribution of random data. And again, we're going to make it centered around 0 with a 0.5 standard deviation and 10,000 data points and plot that out. So again, a randomly generated set of data with a normal distribution around 0. So to find the mean and variance, we've done this before. NumPy just gives you a mean and var function to compute that. So we can just call np.mean to find the first moment, which is just a fancy word for the mean. And that works out to be very close to 0, just like we would expect for a normally distributed data centered around 0. So the world makes sense so far. The second moment, just another name for the variance, and that works out to be about 0.25. And again, that works out with a nice sanity check. Remember that standard deviation is the square root of variance. And if you take the square root of 0.25, it comes out to 0.5, which is the standard deviation we specified while creating this data. So again, that checks out too. Third moment is skew. And to do that, we're going to need to use the SciPy package instead of NumPy, but that again is built into any scientific computing package like nthought Canopy or Anaconda. Import scipy.stats as sp, and then we can just say sp.skew on vals, and that will give us the skew value. And since this is centered around 0, it should be almost a 0 skew. It turns out from random variation it does skew a little bit left, and actually that does jive with the shape that we're seeing here. It looks like we did kind of pull it a little bit negative. Fourth moment is kurtosis, which describes the shape of the tail. And again, for a normal distribution, that should be about 0, and indeed it is. So, the shape of the tail or how sharp the peak is, kind of, if you push it in, it has both effects. So if I were to squish the tail down, it kind of pushes up that peak to be more pointy. And likewise, if I were to push down that distribution, you can imagine that kind of spreading things out a little bit, making the tails a little bit fatter, and the peak of it a little bit lower. So that's what kurtosis means. And in this example, kurtosis is near 0 because it is just a plain old normal distribution. So if you want to play around with it, go ahead and, again, try to modify the distribution. Make it centered around something besides 0 and see if that actually changes anything. Should it? Well, it really shouldn't, because these are all measures of the shape of the distribution. And it doesn't really say a whole lot about where that distribution is exactly. It's a measure of the shape. That's what the moments are all about. So go ahead and play around with that. Try different center values, try different standard deviation values, and see what effect it has on these values, and does it change at all. Of course, you'd expect things like the mean to change because you're changing the mean value, but variance, skew, maybe not. Play around, find out. All right, that's moments. Let's move on. And there you have percentiles and moments. Percentiles, pretty simple concept. Moments sounds hard, but it's actually pretty easy to understand how to do it. And it's easy in Python too. So you got that under your belt? Let's move on.